In this screencast, we're going to consider the titration of 20 mL of a 0.200 molarity solution of benzoic acid with a 0.200 molarity sodium hydroxide solution. Benzoic acid is C6H5COOH, and its Ka is 6.5, 10 to the minus 5, so it's a weak organic acid. Benzoic acid can be abbreviated HA, so the neutralization reaction between benzoic acid and sodium hydroxide can be written as HA plus NaOH, and the products are sodium benzoate and water. If we write the net ionic equation, we have the weak electrolyte HA, the hydroxide, and the resulting benzoate and water, where the sodium cations are spectator ions and cancel out. So this means that in the Erlenmeyer flask, we have a solution of benzoic acid, which is primarily HA molecules with a few hydronium ions and benzoate ions. And then in the burette, we have a solution of sodium hydroxide, which is composed of sodium cations and hydroxide anions. Sodium cations are going to be spectators throughout. We can calculate the moles of benzoic acid that we start with in the Erlenmeyer flask using the 20 mL and the 0.200 molarity. So the moles of HA in the flask at the beginning of the titration is 0.200 moles of HA per liter of solution, and we have then 20 mL of this solution where there are 10 to the 3 milliliters per liter of solution. That means at the beginning of the titration we have 0.00400 moles of benzoic acid. The first point in this titration, where we're going to calculate the pH, is after a total of 10 mL of 0.200 molarity sodium hydroxide have been added. We can calculate the number of moles of hydroxide in this 10 mL by taking the 0.200 moles of hydroxide per liter of solution times the volume, which is 10 mL, and there are 10 to the 3 milliliters per liter. This means that when we've added 10 mL of the sodium hydroxide solution, we have added a total of 0.00200 moles of hydroxide. We've also added 0.002 moles of sodium cations, but those are spectator ions. We can compare this to the moles of benzoic acid that we started with at the beginning of the titration, which was 0.00400 moles of benzoic acid. Since we've added fewer moles of hydroxide than we started with moles of acid, we are before the equivalence point, and the hydroxide is the limiting reactant. So we're going to do a limiting reactant calculation between the benzoic acid and the hydroxide. We have, at the beginning of the titration, 0.00400 moles of benzoic acid. At this point in the titration, we have added 0.00200 moles of hydroxide, and we had, at the beginning of the titration, a negligible amount of benzoate and lots of water. The hydroxide is a limiting reactant at this point in the calculation, so we will subtract 0.00200, which gives us no hydroxide remaining. We will subtract a corresponding amount from the benzoic acid, which gives us 0.00200 moles of benzoic acid remaining. And we will add 0.00200 moles to the benzoate, since that is the result of the reaction of the benzoic acid with the hydroxide. So at this point in the titration, when 10 mL of sodium hydroxide have been added, the hydroxide is a limiting reactant, and so we have left in the flask a bunch of unreacted benzoic acid and a bunch of benzoate that we have produced that has been produced in the reaction. A weak acid and its conjugate base are present in the flask at this point, so we can calculate the pH using the Henderson-Hasselbalch equation. Henderson-Hasselbalch says that the pH is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of the weak acid. The pKa is the negative of the log base 10 of the Ka, which in this case is 6.5 10 to the minus 5. The concentration of the conjugate base is going to be 0.00200 moles over the total volume of the solution. And the concentration of the weak acid is going to be 0.00200 moles over the total volume of the solution. This means that the total volumes will ratio out, and the second term is just then the log of 1. And if you run this through your calculator and round to the appropriate number of significant figures, you get 4.19. We get 2 sig figs after the decimal because there are 2 sig figs in this 6.5 and there are actually 3 in these numbers of moles. The second point in this titration, where we're going to calculate the pH, is after the addition of a total of 20 mL of 0.200 molarity sodium hydroxide. We're going to do this calculation as if we'd gone straight to this point in the titration, and we're not going to reuse the results of the previous pH calculation. When a total of 20 mL of 0.200 molarity sodium hydroxide have been added, we can calculate the moles of hydroxide as 0.200 moles per liter of solution times the 20 mL, where there are 10 to the 3 mL per liter of solution. This means at this point in the titration, a total of 0.00400 moles of hydroxide have been added to the Erlenmeyer flask. We can compare this to the moles of benzoic acid that were in the flask at the beginning of the titration, which was also 0.00400 moles of benzoic acid. The fact that these two moles are equal means that we are at the equivalence point in this titration. When a total of 20 mL of sodium hydroxide have been added to the benzoic acid solution, enough hydroxide has been added to react with all of the benzoic acid. This means at this point in the titration, there is no benzoic acid left and there is no hydroxide left. We can see this by looking at the same type of limiting reactant calculation. We started with 0.00400 moles of benzoic acid, a total of 0.00400 moles of hydroxide have been added. So with the equal number of moles, we have no hydroxide left. We have no benzoic acid left, and we have 0.00400 moles of benzoate, and lots of water. We also have our spectator ion sodium present in the solution, so we have a charge balance. At this point in the titration, all we have in the Erlenmeyer flask is sodium benzoate. Sodium benzoate is a salt of the conjugate base of the weak acid benzoic acid. Therefore, this salt will react with water, will undergo hydrolysis to change the pH to something that is basic. To calculate the pH in a solution of a salt of the conjugate base of a weak acid, we need to do an ice table for the hydrolysis calculation. To do the hydrolysis calculation of the pH, we need the concentration of the benzoate in the solution at this equivalence point. So the concentration of the benzoate at this point in the titration is the 0.00400 moles of benzoate that have been formed, divided by the total volume of the solution, which is the 20 mils of acid that we started with, plus the 20 mils of sodium hydroxide solution that we have added, where there are 10 to the 3 mils in a liter of solution. This means that the concentration of the benzoate at this point in the titration at the equivalence point is 0.100 molarity. To calculate the pH, we're going to do an ice table for the hydrolysis or reaction of water of this benzoate. Benzoate is the conjugate base of a weak acid, so it can react with water to form benzoic acid and hydroxide. Initially, the concentration of the benzoate is the 0.100 molarity. We have lots of water, and we have no acid and negligible amount of hydroxide. This reaction needs to go forward to get to equilibrium, so we're going to subtract X on the reactant side, add X on the product side, and that means that at equilibrium, the hydrolysis of the benzoate gives us an equilibrium concentration of benzoate of 0.1 minus X, an equilibrium concentration of benzoic acid of X, and an equilibrium concentration of hydroxide of X. The Ka for benzoic acid can be used to find the Kb for benzoate. Recall that the Ka for an acid times the Kb for its conjugate base always equals Kw, so the Kb for benzoate is the Kw divided by the Ka for benzoic acid. So we have 1.00 10 to the minus 14 for Kw. We have 6.5 times 10 to the minus 5 for the Ka of benzoic acid, and that is the Kb for benzoate, and it's equal to X for the benzoic acid, X for the hydroxide, and 0.100 minus X for the benzoate. We'll approximate this as X squared over 0.1 and then solve for X. This gives us an X of 3.92 10 to the minus 5, which is then the concentration of the benzoic acid at equilibrium and the concentration of the hydroxide at equilibrium. We can calculate the pH using 14 minus the pOH, where the pOH is the negative of the log base 10 of the hydroxide concentration. The hydroxide concentration then is the 3.9, that should only have 2 sig figs, 10 to the minus 5. And if you run this through your calculator, recalling that these two negatives cancel, the result for the pH is 8.59. For the neutralization of a weak acid with a strong base, the pH at the equivalence point is not going to be neutral because the conjugate base of a weak acid will undergo hydrolysis to make the pH of the solution slightly basic. The last point in this titration, where we're going to calculate the pH, is after the addition of a total of 30 mils of the 0.200 molarity sodium hydroxide. We can calculate the moles of hydroxide that have been added at this point by taking the 0.200 moles per liter of solution, multiplying by the 30 mils that have been added, where there are 10 to the 3, that's the 3, mils per liter of solution. That means at this point in the titration, a total of 0.00600 moles of hydroxide have been added to the solution. Recall that at the beginning of the titration, the number of moles of benzoic acid which were in the flask was 0.00400 moles of benzoic acid. The fact that the moles of hydroxide added at this point is greater than the moles of acid that we started with means that at this point in the titration there is excess hydroxide. We can do a limiting reactant calculation to see this. At the beginning of the titration, we had in the Erlenmeyer flask 0.00400 moles of benzoic acid. We have added at this point a total of 0.00600 moles of hydroxide to give us benzoate and water. This 0.00600 moles of hydroxide is greater than the 0.00400 moles of benzoic acid, and therefore all of the benzoic acid will be reacted away, but only the corresponding amount of the hydroxide will be reacted away. This means we have no benzoic acid left, but we do have 0.00200 moles of hydroxide, and we also have 0.00400 moles of benzoate at this point in the titration. So there are two things that are affecting the pH of the solution at this point in the titration. One is the fact that we have 0.00400 moles of benzoate. It will hydrolyze, react with water to form some hydroxide. We also have an excess of hydroxide. We also have 0.00200 moles of hydroxide that we've added that didn't have any benzoic acid to react with. At this point, which is past the equivalence point of this titration, this excess hydroxide will have a much greater effect on the pH than the hydrolysis of the benzoate. And therefore, we will calculate the pH of the solution using this excess hydroxide. The concentration of this excess hydroxide at this point in the titration will be the 0.00200 moles of hydroxide divided by the total volume of the solution at this point, which is the 20 mils that we started with plus the 30 mils that we have added for a total of 50 mils of solution, where there are 10 to the 3 mils in a liter of solution. This gives us a concentration of sodium hydroxide of 0.0400 molarity. To calculate the pH at this point in the titration with an excess of sodium hydroxide, we'll use that the pH is 14 minus the pOH, where the pOH is the negative of the log base 10 of the hydroxide concentration, which we found to be 0.0400 molarity. This has 3 sig figs, and this has 2 to the right of the decimal, so our answer is good to 2 to the right of the decimal, and that answer turns out to be 12.60. Here is a graph of this titration. We have pH on the y-axis and volume of sodium hydroxide solution added on the x-axis. The points where we have calculated the pH are this one at 10 mils of solution added, this one at 20 mils of solution added, and this one at 30 mils of solution added. This table shows the pH at all of these points in the titration, and so there are some other values that you can calculate to check your calculations for this type of titration.